I forgot to hit record when we started the lecture today. So this is what we missed. We're talking about optimization problems. That's where we have some kind of quantity that we want to find the maximum value of or the minimum value of. For instance, a lot of these come down to area. Given some kind of setup, we want to find the maximum area for something. Or maybe we want to find out how many tickets do we need to sell to maximize our revenue. Or maybe we want to minimize risk in some kind of procedure or something like that. Most of these lend themselves to a picture, and that is going to be our first step for solving these, but not all of them lend themselves to a picture. As you could imagine, if you're trying to minimize risk of something, that's somewhat abstract and they don't always lend themselves to a picture. Some of the homework problems are, they involve just pure numbers. They say the product of two numbers is, find the maximum product of two numbers such that their sum is equal to 5. And it's like, well, how are you going to draw a picture for that? You could if you want, but this is, in general, most of the problems you're giving do lend themselves to a picture. Now, what I did in the lecture was I outlined a bunch of steps that you're going to take every time you solve an optimization problem. And I want to get them out on the board and keep them up so that as we go to solve these, we'll have a nice roadmap, which tells us what we're doing and where we're going. And so that's why I introduced this first. Now, part of the problem is there's a lot of jargon in here and stuff that's not going to make any sense until we go to do our first example. Then it'll make a lot of sense. But I want to have this up there and I want to give this information to you so that you could have it and you could follow along as we do it. So one last thing is that this method for solving these is going to work for most optimization problems, especially when you go into calculus. This is exactly the method that you will want to use for optimization problems. It's just that part number 7 will look a little bit different, but this is exactly what you're going to follow. So, step 1, draw a picture of the situation. If the situation lends itself to it. It almost always will, and the picture will help you a lot. 2, identify the quantity that you want to optimize. So if the question says find the maximum area for something like that, then area is the thing that you want to maximize. If it says you maximize, given such and such, maximize your company's revenue, then revenue or profit or money, dollars, is the thing, the quantity that you're trying to optimize. 3, write a function whose output is the quantity that you're trying to optimize. Okay. 4, write a constraint equation. This will become clear when we do our first example. Right now, what does that even mean? Just wait for just a second. We want to make sure this is up on the board when we go to solve problems, but you'll see what that is in a minute. Okay, number 5, use the constraint to turn the optimization function into a one variable function. Again, what? Well, what you'll see, this ends up being like, especially like with area, we'll end up with something like area equals x times y, or base times height, or something like that. The problem is this thing is a function of 2 variables. There's an input x and an input y. We don't know how to deal with functions of multiple variables yet. And so, and even when you go to take calculus, you won't know what to do. And this is what you will want to do. You'll find a constraint equation that will let you turn this from a function of 2 variables down into a function of 1 variable and 1 variable only. So that's going to be step number 5. Once you have your 1 variable function, step 6 is to graph the function. This will help you so much if you can graph the function. It'll help you not only to conceptualize what you're doing, but it'll also help save you from making mistakes. And sometimes that's big. So step 7 is find the min or the max. So you've done step 6 and you have the function that you're trying to optimize. In this case, it looks like we're trying to find a max. And the only functions that we know right now how to optimize, or the functions that we know how to find mins and maxes, are parabolas. And so in our class, this step right here, finding the min or the max, is going to be the same thing as finding the vertex of a parabola. We know where the x value of a vertex occurs. It's always at minus b over 2a if it's written in standard form. And therefore we could find the output value by plugging whatever that is into our function. And we'll talk about there are other ways, and we want to do it multiple ways to check our work. But this is the idea, right? That in our class, the only functions we know how to find mins and maxes of are parabolas. And so this step reduces down to just find the vertex of a parabola. But in general, and when you go to take calculus, you will learn methods for finding mins and maxes of any function. And so later on, when you are taking, we'll just say in calculus, this step, this outline will be exactly the same. The only thing that's different is that this procedure will be slightly different. But you're still, when you go to do any optimization problem, you're still going to go through all these steps to get down to here. And so then once you've found the min or the max, we're going to use the function and the constraint to identify all the desired quantities. And in this class, I'm going to demand that we identify all the possible quantities. Even if the question only says to find the max area, I want to find everything about the problem. And again, that's going to help prevent us from making mistakes and help us to check that everything we've done does indeed work out and we haven't messed something up somewhere along the way. So I know a lot of this sounds like crazy jargon stuff like constraint equation, turning a function from multiple variables down into one variable, identifying desired quantities and stuff like that. But when we do, I want all this information somewhere on your paper so that when you're following along with the example that we're about to do, you can have it written down and you can match it up as we're doing it. And that will help explain exactly what all of these things mean. It will all become clear in just a minute. And so the first question we are going to work on, you're going to see it pop up on the board in just a second, but then I erase it right away because that's where I started recording. But this is what it says. A farmer has 40 yards of fence. She wants to enclose a rectangular area along a river, that is, where one side of the fence is on the river, like that. And so we only need 3 sections of fence, this part, and this part right there. So one side of the rectangle will be the actual river. The question is, what is the maximum area that she can enclose? What is the maximum area she can enclose? So we're going to get rid of all this. All right, so let's draw the river first and do that in green. Here's the river. The farmer is enclosing a rectangular area. So in general, rectangles aren't squares, so I'm just going to exaggerate the way that this looks. This is then the fence, right? This is what I'm imagining in my picture. We have 40 yards of fence that start here. They come down, they go over this way and go up. Okay, now part of drawing a picture, and anytime we're dealing with lengths and stuff like that, we want to label everything, right? Since it's a rectangle, there are two of these. There's, I guess we could call it like a height and a width. We're much more familiar with using X's and Y's than we are with H's and W's. So I'm kind of partial to using X's and Y's to label my lengths. So what I'm going to do is just say, okay, then this right here is X. I'm going to say that the width here is X and the height is Y. If you prefer L and W or whatever, H and L or H and W, that's fine too. There's no difference between anything we're going to do. I just prefer X's and Y's, so that's what I'm going to do. Okay, so if that's the case, what is, okay, I think we have everything for the picture right now. This is what the thing said that the farmer is going to do. We're going to build a rectangular area right here. And one of those, one of the walls, we don't need fence because it's bounded by the river. And so, yes, we have 3 bits right there. So let's move on to ID, the quantity that we want to optimize. What is the thing that we want to optimize? What did the question say that we want to find the max what? Find the maximum what?
Quantity?
Say what?
The maximum area that she can enclose, right?
Area. So area is the quantity that we're trying to maximize. So we want, so this is part 2. We want to maximize area. That is area. So that's part number 2. We've ID'd the quantity that we want to optimize. Okay, we want area. So we want to write a function whose output is area. How do we calculate area with our scenario? What is the area of that box?
Y.
Say again? I can't hear you over this boy. He is just blabbing.
Isn't it X times Y?
That's it. That's area, right? Like the length times the height or whatever, right? Like the 2 dimensions multiplied by each other, that is area. So for problem number 3, we're writing a function whose output is area. In other words, we have area, you just told me, is equal to X times Y. Here's the problem. This is a function whose output is area, but there are 2 inputs, right? And just bear with me here. Right now, we have a function of 2 variables. X and Y are my inputs, and my output is the thing that I want, area. Problem is, we don't know how to deal with functions of 2 variables. And even when you take calculus, you're not going to do that for a year. Like you're going to take, well, actually, if you're doing it in high school, it'd be 2 years of calculus before you learn how to optimize functions of 2 variables. Like, so what we're going to do, and this is the idea here, looking ahead of what we're about to do, we're going to find an equation, a constraint equation, that's going to turn my function of 2 variables into a function of 1 variable. This is a common theme of things that you're going to be doing in math for a long time, is take a problem, and how many times have I said this? You take a problem you haven't seen before. I don't know what to do with a function of 2 variables, and we need to turn it somehow into a problem that we've seen before. Because if we're kind of hoping here that what's going to happen is we'll have a function where area is the output, and it's hopefully going to be like a parabola, and then we'll be able to find a max or a min. Because we know how to find the max of a parabola, it's at the vertex. So that's kind of the idea with these next steps, is we have something we haven't seen before. We have an output of something with 2 inputs. Maybe somehow we could turn our function of 2 inputs into a function of 1 input. So we do that with step number 4 will get us to that. So a constraint equation. What we want to do is find some other way of relating these two variables together. And right now, what was the only other information that was given in, or rather, what was the first thing? What was the first thing that was given? Or just what was the other thing that's given in the prompt for the question?
40 yards.
40 yards of fence. So let's think about this. And this is where our picture is going to really help here. I imagine, and this is how I like to do this kind of question, is like if I'm just going to go out and lay this fence, that means that if I walk from here to here and lay down, I don't know, fine. Let's just think about this actually. So here we go. So I'm going to start walking right here. And let's say that I lay down 2 yards of fence here. Well, that actually determines how much I'm going to do over here, keeping with the picture. That means that this is 2. Okay. If that's the case, how much fence would I have left? If we have a total of 40 yards, what would this be from here to here?
20.
20. So let's think. 20 from here to here, and then a +2 for there, and +2 for, yeah. What would that be? You have 40. You've laid down 2. So how much do you have left?
38.
38. Then you lay down another 2. How much do you have left?
36.
36. So here's a possibility. Maybe that's something we want to do. And let's just think about this. Walking from here to here, we'd lay down 2, then we'd lay down 36 for a total of 38. And 39, 40 would be 40 yards of fence. Another thing we could do, just real quick, is we could see what that area is. Let's see, the area would be 2 times 36, which would be, 6 would be 12, I guess, 72 square yards. Okay, let's see. I'm just kind of playing with this because this is just a guess. Now, what I'm doing right now has nothing to do with this. We're just kind of playing around with the idea right now. Another thing I could do, what if I went down by 3 yards? Let's say instead I went down 3, meaning that I'd have to go 3 right here as well. Then how much would I have left to play with right here?
34.
I think 34, and let's just check that. 34 plus 3 would be 34, 5, 6, 7, plus another 3, 37, 38, 39, 40. That would be a total of 40 yards. My area would be 3 times 34. 34 times 3 is 12, and 1 is 90, 102. Oh, and look at that, 102. It's actually bigger that way. So let's think about this now. What am I doing? Right now I'm just playing with stuff, but I'm also noticing something here. If I made these really small, right? Like if I made the width really small, like 1 and 1 right here, I guess I would have 40 minus 1 minus 1. I would have 38 left over. My area would be 1 times 38 would be 38. That's not very big. But if I made this a little bit longer, I have 2 times 36, which is 72 yards. That's even bigger than 38. I would have a bigger area. But if I kept going with 3 in this direction and 34 this way, I have 3 times 34 is 102. That's even bigger. But I'm going to run into a problem. Like you might think, oh, just make these as big as you possibly can. Well, let's try that. Let's make those really, really big. Let's go let's say that I made my lengths really big. Like, how about, hold up. What if I made it 19 and 19 on either side? How much would I have left to play with down here?
Two?
2, I think. Yeah, I think you're right. It took me a second to do that. But yeah, that should work, right? 19 and 19 is 20, 38, 39, 40 would be 2. Okay, so let's just see what that would be. 2 times 19. 2 times 9 is 8, and carry the 1, and 1 times 2 is 2, and 3, 38. Oh, I'm back down to 38. You kind of see what's happening, right? Like when this is really, really skinny, we're down at 38. Make it a little bit bigger, it jumps up to 72. Hey, that's a bigger area. That's what we're trying to maximize. We make that even bigger and we get up to 102. And if you keep stretching though, right, we end up getting less area. There's got to be some kind of sweet spot in there. And that's what we're trying to find. That's the idea behind this. We want to maximize the area. Like you kind of think about this. This is what the farmer was first thinking. Like, well, I don't know. Maybe I'll go 2 by 36 would look nice. What do I have? Yeah, but maybe I want to do 3 and 30. Ooh, I'd have more. I'd have more area if I do it this way. Maybe there's a sweet spot somewhere. And that's what this idea is. We want to maximize that. We want to find that sweet spot. You'll notice something interesting. Remember, the idea was we have a function of 2 variables, and we wanted to take that and drop that down to 1 variable. And in each one of these cases, I just chose 1 length, and that determined what that length had to be. When I said this is 2, well, that means that's also 2. That means you only have 36 left over. When I said that's 1, that's also 1. It had to be 38 left over. When I said that there's 3 here, there has to be 3 here, and that's 34 left over. These things are determined, they are constrained, right? One variable is constrained by the other by the fact that you only have 40 yards to work with. And that's what we're going to use right here. And to put this mathematically, let's think about it this way. So I'm going to get rid of this. We're going to say, okay. This total perimeter right here is constrained to be 40 yards. And so how could I write that in terms of X and Y? 40 has to equal what in terms of X and Y? This is where I like to use my stick figures. So I imagine, and this is how I like to do it. We have Y yards right here. We have X yards right here, and we have Y yards right here. I imagine that I'm the farmer and I'm going to walk from here and lay down fence all the way around. And so by the time I've walked from here to here, I've laid down Y yards of fence. And then I'm going to walk from here to here, and I will have laid down an additional X yards of fence. And then I'm going to walk from here to here, and I'll lay down an additional Y yards of fence. And so my total yards, or my perimeter here, is Y plus X plus Y, like that. In other words, how can we write that even simpler than that?
2y plus x.
2y plus x. There we go. This is a constraint equation. It constrains, right? Kind of like we were seeing before. If you choose a y, it determines what x is. We could have played it the other way around. We could have said, hey, if x is 20, what does that force y to be? Well, let's say if that's 20 and those have to be, I guess 20, those have to be a total of 20. Those would have to be each 10 right there. And you'd say, yeah, that makes sense. You go 10, you've gone 10. Then plus 20 would be 30. You go another 10, now you're at 40. And that's the total amount of fence that you have. So that's what we mean. We are constraining x and y. They're no longer free to be anything. And they never were in the first place, right? When we chose a value of y, it determined what x is. Conversely, we could choose a value of x and it determines what y is because we're constrained to only using 40 yards of fence. Okay. Does that make sense how I got that?
Yes.
Okay. So now this is where it starts to get a little abstract. We've drawn a picture. Cool. We've ID'd that we want to maximize area, which means we want a function which the output is area. So we did that. We said that in this case, with these letters, x times y is the area that we want. Okay. We've identified a constraint equation. These things were not free to be whatever they want to be. I can't just take one of them to be 40 and the other one to be 40. Because we don't have that much fence. We're constrained by the amount of fence that we use. So we've written that using the variables right there. Now, step 5 is use the constraint equation to take your function of 2 variables and drop it down to a function of 1 variable. In other words, this is a fancy way of saying, solve this bad boy for one of the variables and then take that and substitute it into that original equation. You could do this either way you want. You could solve for x and plug it in, or you could solve for y and plug it in. Let's get y by itself. So I'm going to do this. You do it on your paper. Solve this equation for y and tell me what you get.
And this is step 5, yes?
Yes, this is step 5. We are using our constraint to reduce our 2 variables down to 1 variable. In other words, we're writing 1 variable in terms of the other variable. And what do you get? Did you get y by itself?
Yes.
So what did you get?
That.
You got that. Cool. Like, and now another thing to notice is like you could have gotten this, and that would be perfectly fine. That would also be perfectly fine. You could leave it like that and plug along like we're about to, and eventually you will end up writing it in a different way. But that's fine. If you have it like that, that's perfectly good too. So, okay. Still on step 5, And the idea is if we could turn one variable into the other variable, in other words, we use our constraint to get one variable by itself, then we could just substitute up here and say, well, y is equal to 20 minus 1/2 x. So instead of writing a equals x times y, I could just say, well, then a is equal to x times 20 minus 1/2 x. And now we have a function where the input is one variable, x, and the output of that function is the quantity that we want to optimize. The output of that function is the area. And that's the thing that we're trying to find the maximum. We're trying to find the biggest bang for our buck here. Okay. So are you tracking? Are we done with step 5?
Yes.
Now let's graph it. A few ways we could do this. The thing to notice here, I could rewrite this. There's a few ways we could do this. In fact, I'm going to go ahead and distribute this guy in and get 1/2 x squared. And I'm used to writing my squared term out front. I like to go minus 1/2 x squared plus 20x. Now, one thing to notice is if we were, first off, this has to be a downward facing parabola because the a term is a negative number. So it has to be a downward facing cup, which is what we hope for. Part of this step, and we don't have to graph this perfectly. In fact, it doesn't have to look, we don't even have to use axes really, but I'm going to. The idea is that it's a downward facing cup. That's what this says. And that's what we hope for. If we're trying to find the maximum area, it had better look like this. Because if it were the other way around, we'd be kind of screwed. Maybe we'd be able to find a minimum area, but maximum, well, you could just keep going forever and ever. What we're hoping for, right, if this output here is area for an input value of x, we hope that this is a downward facing cup, and then we could find the vertex right there. Okay, so the graphing, you don't need to worry about doing it very well, but one thing to notice is that when this guy is factored, it's easy to find the zeros. And I could see that that it has to go through right here. Right? Because one of the zeros of it is 0. So it has to look like that. And if I were so inclined, I could say, well, the other 0 is when 20 minus 1/2 x is equal to 0. Or when 20 is equal to 1/2 x, or when x is equal to 40. And let's kind of stop and think about this. Does this make sense? If x is 0, my area is 0. Well, yeah, if x is 0, then I don't have any area, right? Like the fence that I'm trying to build will be just a line like that. 0 units over that way and right back, yeah, my area would be 0. Similarly, if x were 40, we'd have 40 in the x direction, but then we'd have nothing left for y, and so we wouldn't have any area that way. It would just be a line 40 units long, so 0 area, and that's what that says. If x is equal to 40, then the area, in other words, the height of this graph is 0. If x is 0, then it's just that guy right there. And this says that, yeah, the area would be 0. So this matches pretty well with my intuition. This also matches with my intuition from earlier, which is like the bigger, or rather, yeah, remember how when we were playing with the different sizes here, right? wouldn't do that. It would do like this. As we were playing with these different sizes, we saw that there should be a sweet spot somewhere in between where you get the most bang for your buck. You get the most area for some given value of X. And that's what we saw earlier. It actually makes a lot of sense. So now we're done with 6. Now we need to find the maximum value. How do we find the max on a parabola?
Okay.
It's at the vertex. That, I'm going to call it x sub v. The x value of the vertex is at where? In terms of a nifty formula we have, what is that?
Minus b over 2a.
Minus b over 2a. So you plug in your b and your a and you tell me what you get.
No. Zero. Who's sleeping? Oh, yeah. Means. That means. That means. That means.
Yeah. She's working right now.
Sleeping.
No, she's working on something.
Sleeping.
She's doing math.
Yeah.
Wouldn't it just be 20?
Yes, exactly. Exactly. Now let's look at this. My formula for the x value of the vertex, or for the input value of the vertex, is minus b over 2a. This is my thing. My a is -1/2. My b is plus 20. I can just plug that in. Minus b would be minus 20 over 2 times -1/2. -1/2 times 2, the 2's cancel out. I just have a -1 in the denominator. I have a -20 in the numerator. I have 20 right there. This happened to be one that went through here at 0, right? When we found the zeros of this parabola, one was at 0, one was at 40. It happens to be, it always has to be, halfway between the 2 zeros. And what do you know? Half of that is that. I'm tempted to just say, whenever you have one of these, you could just take half of that. But the thing is, if you start doing that, like, you might get in the habit of doing that, and then one day you have a parabola that doesn't go through here at 0, and then you're so used to just looking at this number and saying, oh, it's half of that number. And if it were, say, shifted over to 10 and 50, you go, oh, half of 50 is 25, so it has to be here at 25. No, well, it's halfway between 10 and 50. It's not 25, it would have to be 30. But it's not, just saying, it happens to be in this case that it's half of that number, but it's always halfway between these guys, which, what do you know, is that bad boy right there. So I think this is a pretty good way of just in general, if you have an equation or a quadratic and standard form like this with an A and a B, you could just say, well, that's that guy right there. Alternately, if you'd like, you could complete the square, but you'll end up doing exactly this thing right here and getting that. So any way you want to do it, yes, 20 is that value. Now, so many students that I've worked with over the years, they get to this point and go, oh, 20. And then they write down 20 as their answer, and then they're done. And that's not what was asked for. They didn't ask, you're so used to solving for X, right? Like that's what we've done for years now in math is like, oh, once you get X, you know that X equals 20, you're done. No, that's not what was asked. We want to find, we were told to find the maximum area that they can enclose. Now, we found the max of the function. And if we're so inclined, we could just take that, plug it into here and find the final value. But what I'm going to say is for all of these that you do, every single one of them, I don't care what they've asked for. I want all quantities written down. Now that we have an X, I want to know what X is. I want to know what Y is. I would like it written out. And finally, then we're going to find what X times Y is. So that's what I mean by step number 8. Use the function and the constraint to ID all the quantities. Now, one of the quantities, yes, is area, and that's all they ask for in the problem. But why don't we just go ahead and knock it out? Like we're gonna identify everything. So if we know that the sweet spot is X equals 20, I'm gonna have that written down somewhere so that I don't mess this up. I'm also going to erase some of this work I did down here to give myself some room. Now, what's nice about this, and you'll notice this, you could find the other variable really easily, right? Because in every one of these questions, you will have solved for one variable in terms of the other. And then once you've found one of them, you could plug it back into your constraint equation to find the other. So let's do that. Let's take X equals 20, plug it into our constraint, and see what Y equals. So I get Y equals 10. I took my X equals 20, plugged it in. 1/2 of 20 is 10. 20 minus 10 is 10. And so Y equals 10. So finally, I'm going to go and put this all together back with my original picture. I'm going to say X equals 20 right here. Y equals 10. Finally, the thing that I was trying to find out was what is the area. And now this is actually pretty easy to do. I could just say, well, the area is X times Y. X we know is 20. Y we know is 10. And so the maximum area that I could get is 20 times 10 is 200. And that's the answer that we're looking for. Now, alternately, can I get rid of this? You got this right here?
Yeah.
Okay, so another thing we could have done, like I said, the only thing about this the only quantity that was asked for was area. They didn't bother to ask us what the to identify all the different ones, but I want us to do that. What we could have done once we got to that point where we found that the vertex occurs at X equals 20 is we could have just plugged that in right here, because that's what this is. This is the graph of A of X. In other words, for any given X, you could find the area right here. And we could have just said right at the beginning, well, since that's all I'm looking for, I'll just plug in a 20 into here. And we get negative 1 over 2 times 20 squared plus 20 times 20. Oh boy. And we'd have, okay, negative 1/2. 20 squared is 20 times 20 is 400. Plus 20 times 20 is 400. Half of 400 is, and it's a negative, so negative 1/2 times 400 is negative 200. Plus 400 does indeed give me that right there. It's not too bad. It's a little bit convoluted, but since it's nice to have a big picture at the end, sometimes it'll be easier to just do it that way. Like I did the original way, I got my A equals 200. So now we're done. We've identified everything. We've used the function and the constraints to identify all the possible variables after finding what value of X makes that work. Another thing, just notice, this is what the interesting thing about the constraint, right, is like I plugged that into that right there. But you'll notice that that's exactly what we were doing, like at the beginning, right? We had it, given one of them, we could have just said, wait a second, if that's 20 and those are equal, if you've gone 20 and you have a total of 40, well, then those have to be 40. Or I mean, I'm sorry, in order to give you a total of 40, you're going to need, well, 20 plus 20. And so those together have to be 20. So half of those would be 10 each. And then you'd have a total of 10 and 20 and 10 makes a total of 40. And that's what you're looking for. But isn't that exactly what that means? Right? Like that, from the very beginning, the constraint existed. We put it into mathematical language here, but it's just kind of interesting to note that that is what my brain just did right there, right? But I did it kind of in a convoluted way. But anyway, so that's the idea with these min-max problems, or with the optimization problems, is we go through them like that. I hope all of this now makes a lot more sense what I mean by the constraint equation and dropping something down to equal two variables. Really, I could have said this in very elementary language. I could have said, you know, use your two variables to get one variable in terms of the other, substitute that back in. But I want to keep this as general as possible, because when you go to do this in other settings, which you're going to do all the time in calculus, these rules, these steps are exactly what you're going to do. And it's nice to have it like that. So, okay. Boy, it's getting late. So, did that make sense?
Yes.
Okay. Do another example like that. Farmer wants to build a fence. Rather, farmer has, again, 40 yards of fence and wants to enclose a rectangular garden. What dimensions will maximize the area? Almost the same thing, but now we're not doing this up on a against a river or anything like that. Okay, so let's draw a picture. Rectangular fence. All right. There it is. All right, let's label some sides. You want to do it the same way that we did before? X's and Y's?
Okay.
Let's do it. So let's do this one as X. This one is Y. Okay. Do we have everything we need for the picture? Yeah. I mean, there's nothing more to a rectangle than one side and another side. That's it. That's everything that we need to know about a rectangle. Okay. What is the quantity we want to optimize?
Area.
Area. And do we have a formula for area given what's on the board?
XY.
XY. So we have a function. Takes two variables as an input and gives us area as an output. Okay, it looks like we have part 3 done. Now, what about a constraint? How are we going to constrain this? What are we constrained by?
40 yards.
40 yards. And in this case, 40 yards equals what in terms of X and Y? Think about walking around that guy. How long would you be walking?
2x plus 2y.
2x plus 2y. There we go. All right. That looks good. I think we got our constraint. Okay, so use your constraint to turn your function of 2 variables into a function of 1 variable. In other words, solve this bad boy for one of the variables. Which one do you want to get by itself?
Hold on.
Okay.
Up, 3, down.
I want it to be organized and I miswrote something.
That's cool.
Oh. Okay.
Okay. Which one do you want to solve for? Which one do you want to get by itself?
Y.
Sure. All right, you do that. I'm gonna get something real quick. And you tell me what y equals. Did you
Yeah.
get that?
Uh-huh.
Okay, so let's use that to turn our function of 2 variables into a function of 1 variable. So x times y is the same thing as x times 20 minus x. What's nice about that, graphing that guy makes it really easy because I see where the zeros are. I could see that when I plug in a 0 for x, I get a 0 for a. I see that when I plug in a 20 for x, I get a 0 for a. So that must be where the zeros of this parabola, and I could tell it's a parabola. That's where they live. Another thing I could see is that if I distribute this bad boy into there, we have negative x squared plus 20x. And so that's a downward facing parabola, right? The negative x squared makes it a downward cup. And so this guy's got to come up and go back down like that, which is good if we're trying to maximize the area. This part 6 here is not strictly necessary, but it really helps you believe, or it can help you catch yourself if you're not on the right track. So I'm going to require that we do it every time. And I'm starting to feel good about this. Now, one thing I could do is say, well, it's halfway between, right? What's halfway between 0 and 20?
10.
10. Now let's just double check that using my vertex formula. We know that the x value of the vertex occurs at something over something. And when I plug that guy in, I get. Oh man, he is so cute. He's singing the Sesame Street song. Oh. So I can see that half of that distance is 10, but I could also, and I want to verify this because I don't trust myself. I'm serious. When I do these, I don't trust myself. And I want to say, okay, let me just make sure here. Negative b over 2a. Negative b is positive 20, so I plugged it in. Okay, 2 is 2. Negative 1 is a, so I plug that guy in. I get negative 20 over negative 2. Negative 20 over negative 2 is positive 10. Okay, I feel good about this. This is the x value for which the max occurs. That is not the maximum value. That is the x value for which the max occurs. And if I were so inclined, I could go ahead and just solve the problem altogether and say, well, let me just plug that in because I have a function a of x is equal to, so when I plug in an a of 10, I get negative 10 squared plus 20 times 10. Negative 10 squared is negative 100. 20 times 10 is 200, and 200 minus 100 is 100. And so my output or my max value of area is 100. That's one way of doing it. But since we're going to be getting all of this stuff anyway, let's go ahead and do that. So if x is equal to 10, what does y have to equal? Got to use our constraint for that. Did you say 10?
Yeah.
Yeah, I think this guy's yelling. I can't hear very well. But yeah, all I'm going to do is take that and plug him back in. 20 minus 10 equals y. 20 minus 10 is 10. So 10 equals y. All right. 10 equals y. And so y is 10 and 10. And I could just kind of double check everything that I've done. I like doing it both ways simultaneously to make sure, because if you get to the end and you go, okay, x is 10 and y is 10, and you do that, and then you go, okay, 10 times 10 is 100. And if you get something different than you got earlier, you know you made a mistake somewhere. It's a nice way to check and make sure that everything's coming out. And so that's kind of part 8. That's why I do part 8. And I'm going to demand that we always do part 8, is to check that everything comes together and we haven't messed anything up. And so finally, and oh, I'm sorry, no, the actual question was what dimensions will maximize the area. So we did need to find these right there. And so in this case, we didn't need to find what the area was, but I'm going to require that we do find that quantity because it's nice to have everything complete. It also helps us check our work. And so finally, the dimensions that will maximize the area are when the width is 10 and when the length is 10. In other words, the way to maximize a rectangular area is when you have a square. A square maximizes a rectangular area. And that kind of makes sense, right? Because if you had a really long, skinny rectangle, 1 by, in this case, 40 would have to be what? 19 and 19. Yeah, we saw that one earlier, right? 1 times 19 would be 19. And if you started compressing it in, and once you compress it past a square, it's going to start to get long that way, right? And that's what we're seeing here, right? That there's a sweet spot right in the middle. And that happens to be where both lengths are same. Notice that we had a rectangular area last time, and the maximum area was not a square. That's because we were constrained. It wasn't nice and symmetric. We weren't free to take the entire thing. We were constrained to only 3 sides. And so when that's the case, we end up with something that's not a square, which I wouldn't have expected. I would have expected, well, a square, right? For the last problem, but that's not the case. So any questions with this? Is this flow making sense?
Yeah.
So when you go to do this in more general terms, what's going to happen, like when you take calculus, is the exact same thing. The only difference is when you get down to here to graph your function's going to be crazy and it's going to look like this. But you're going to have a way of finding the mins and the maxes. You'll be able to say, well, here's a min, here's a max, here's a min, here's a max, and et cetera, et cetera. But the flow is exactly the same. You have a bunch of variables, you have a function of a bunch of variables, you drop it down to one variable, you graph it, you do whatever you need to find where the min or the max is, put it all back together at the end. Okay, so that's optimization in general. That's the flow for that. You are going to have questions on that, homework questions. And yeah, you're going to have a bunch of those. And they're all pretty much the same thing. The only thing that's going to change is you're going to have some questions that's going to say, for instance, what is the maximum product of two numbers whose sum is 227? Or I'm sorry, whose sum is 22? In that case, we don't need a picture, right? But everything else is the same. We're trying to, the maximum product of two numbers. It's the same thing, right? It's exactly the same thing right here. And it says, whose sum is 22? Oh, x plus y equals 22. That's your constraint. And you have the exact same steps to do that. There's no difference there. I did not give you that one. And we want to make a note of that. Okay. Finally, we're going to go back to 8.2 real quick because there were some word problems involving word problems that lead to quadratic equations. And most of them are pretty straightforward. You'll have stuff like, yeah, in every case, if you draw a picture, it will make your life much, much easier. But there's one kind of problem. You've seen it before. We've done this thing before, but it could really trip you up if you're not thinking about it. And here's an example of one of those problems. It is from page 349, number 10. It says airplane. Airplane A excuse me, it travels 2,800 kilometers at a certain speed. Oh, this one sucks. Airplane B. travels 2,000 kilometers at a speed that is 50 kilometers per hour faster than A. Already, and we've done stuff like this before. We have different speeds and stuff like that. I'm already thinking, I'm going to let the speed of airplane A be S. And then it says that B travels at a speed that's 50 faster than the speed of B would be S plus 50. This is like what's already going on in my head. So we've seen stuff like that before. And so we'll see. It says that much faster than today in 3 hours less time. In 3 hours less time. Find the speeds of each. So my idea here as I started reading this was like, yeah, this is the kind of thing that we're dealing with. And anytime we're dealing with speeds and distances and stuff like that, I think that the rate is equal to the distance over time, or that rate times time is equal to distance. And so if we start puzzling this thing out, it says that airplane A travels that much at a certain speed. So I like to draw that out. We're going to say 2,800 kilometers at a certain speed at S kilometers per hour. The other one travels 2,000 kilometers at a speed of S plus 50. In 3 hours less time. And so I'm thinking we could relate these things via time, probably. And so let's think about this. It's going at a certain speed. This one's going at a certain speed. And let's just say that this does it in T hours. Then this one, it says it's doing it in 3 hours less. And so in this case, it would be T minus 3 hours. So that's how long that took. Another thing I didn't solve for, but we can, is to get the T by itself. That would be that time is equal to distance over rate. Nice to have those on your page whenever you're working with this kind of stuff. And so I'm seeing, okay, we have a distance and a rate. We have a distance and a rate, and we have times here. So kind of putting this together, I'm going to say, well, distance over rate, right? So in other words, 200, I'm going to just do it this way. Distance over rate is 2,000 divided by S plus 50 equals the time that it happens. In other words, equals T minus 3. Okay, kind of putting that together. Here we have distance and a rate equals a time. So distance 2,800 over the rate, which is S, is equal to T. And we could say, well, hold up. If T equals T, and if you remember back to how we did this before, if T equals T, then we could relate these two equations together. The only difference here is T is not by himself, but that's an easy fix. We could add 3 to both sides and get 2,000 over S plus 50 plus 3 is equal to T right there. I just took that and turned him into that. We have this guy is equal to T, and then we can solve. Because I'll say, wait, if T is equal to T, then that is equal to that. And so it's kind of the same thing. We've done this stuff before. That's why we're not going to go really into it. The only difference, and the reason why they wait until now to do this kind of stuff, is that the thing that you're going to get when you go and solve this, when you go 2800 over S is equal to 2000 over S plus 50 plus 3. When you go and kill your denominators and do all that stuff, you're going to end up with a quadratic. You're going to end up with some kind of AS squared plus BS plus C equals 0. And well, we know how to solve that now. So it's stuff you've done before, and they're terrible. Distance, rate, and time are just terrible. But the only difference is that the thing that you end up with in the end is now a quadratic. And so it's nothing new. You've seen it before. You've done them before. But the thing that you end up with is now quadratic. But we know how to solve quadratic equations now. So that's why they're being reintroduced. In interest of time, there's another type of this distance and time question, distance, rate, and time question that you will run into. But there is an example on page 348. It's example 2 that pretty much lays out exactly what you're going to do for that kind. So I would say definitely read that bad boy. Look at that. That will help you with the homework. But again, all of this, you've seen all this stuff before. You've done it before. I'm not saying it's easy. This is wicked hard stuff, but it's doable. And the only difference is the thing that you end up with in the end is now a quadratic instead of something that just has one variable that you could solve for or get by itself. So, okay, you ready for your homework?
Yeah.
Okay. Let's get this. Okay. 348. Okay, so homework. And this will be due Wednesday at 8. So you have a long time to do this. It's not that long, but it's difficult stuff. So you have a lot of time to do it. This will be due Wednesday at 8 a.m. So from section 8-2, chapter 8, section 2, on page 349, you're going to do number 1, 3, 5, 7, and 9. Chapter 9, section 6, on page 410. 13, 15, 17, 21. I'm going to put a star right there. Don't let me forget what that's about. I'll tell you about that. Finally, one last question, and it's from 9-8. On page 419. Number 16. It's almost exactly the first problem we did. The wording is a little weird. They say 2, it's the same thing as a river, and you're building a fence using a certain amount of fence, but they say you're going to build 2 adjacent rectangular enclosures. They don't mean rectangular enclosures that are separated. They mean 2 rectangular enclosures that touch each other. In other words, the picture that you should end up with is something like this. And so the perimeter will be something like this, just like what we've worked on. The only difference is you have an added little bit that comes up like this. It's the same problem.
Mm-hmm.
One little difference. So, okay. On 21. Oh man, I had it right here. Come on. For 621. Yes. Okay. It says to use a calculator to find the min or the max for each problem. Yeah, use a calculator. The reason that they're saying that is because it looks like this. It's like 8.2x squared minus 38.7x plus 41.7. They're ugly. And so they're saying, do what you know how to do to find the min or the max of this guy, but use a calculator to calculate it. They're not saying like graph it and estimate. They're saying you should know how to find a vertex of a parabola and use a calculator to estimate or to do that, but don't graph it and estimate. Just want to make that clear.